All right, welcome guys. This is going to be section 3.2, our second one of chapter 3. And unlike the previous ones, this is going to be a bulky section with new content. You know, most of the stuff we've been doing to this point is not very complicated or it's relatively new. But this section 3.2 is going to be a lot of new stuff. It's going to be very formula heavy stuff, and it's going to be pretty different from anything you've probably ever seen before. Now, don't freak out. It'll be fine. We'll walk through it together. I'll try and go through it nice and slow so it all makes sense. But please take good notes, follow along here, write down definitions because most of the stuff will be new. All right, so let's talk through it together. What is 3.2 all about? Well, 3.1 was all about measures of central tendency. What are those? That's averages. That's finding the middle of the set of data. That's finding a number that we can summarize our data with. But in 3.2, we are going to learn about variation in data. You see, it's not only important to be able to summarize data, but I want to know how consistent my data is. How much does my data vary from one number to another? A very simple example is, let's say I try and attempt 3 30-yard passes. In attempt number 1, I hit 30 yards each time. In attempt number 2, or a different quarterback, maybe they throw 10 yards, 30 yards, and 50 yards. Well, if you calculated the mean for both sets of data, you're going to find that the mean is 30 for both. But if you would calculate the range or look at the variation, or you just eyeball it, you're going to see here that the first person was much more consistent. So while both may average 30 yards a pass, I obviously want to go with quarterback 1. What's the point in this illustration? Variation and spread of data is important. Almost as important as what is the average in data. Okay? So we are going to learn in 3.2 about measures of variation, and we will use them for the rest of stats. We not only care about what the average of the data is, but how consistent is it. While averages attempt to take data and summarize them into one number, variations are going to look at how widely dispersed the data is, or the spread of the data. Again, this lesson is going to be all about variations, how widely dispersed the data is. Okay, so what are some examples of measures of variation? We know mean, median, mode are measures of central tendency. Well, how do we measure variation? Well, one of those measures is range. And now you actually probably will be pretty familiar with what the range is. The range is the difference between the largest and the smallest data value. Let's look at an example. Let's say I was attempting to throw more passes. Unlike mean, median, and mode, which is going to attempt to summarize my passes, the range will tell me the distance between my longest throw and my shortest throw. And this can tell me the width of my data. But it isn't still what we're looking for. You see, we want to know variation in data. And just like I illustrated with mean earlier, range can fall short in doing that. If you look at both of these lists, again, by eyeballing it, you would tell me the first list is more consistent around that 22 marker than the second list. But they both have the same range. So even though they both have the same width, the data does, it still isn't giving me range doesn't give me an accurate representation of how consistent that data is. How much does it vary from one value to the next? Okay, so range is good for the width, but still not how much it varies. So the question obviously begs. Standard deviation, or what is it? What is this measure that can tell us how consistent data is? In stats, we are going to use standard deviation. What is standard deviation? It's a measure that is used to quantify the amount of variation or dispersion of a set of data values. This will be our measure for consistency. This is it. This is the formula. When we find the standard deviation through a number, we are able to tell how spread out or tightly packed the data is, how consistent or inconsistent it is. Okay? You can see it bolded here because it's incredibly important. From this day forward, we will be using standard deviation almost every day. And every statistical study we look at, every statistical measure we analyze is going to have standard deviation as an integral part of it. Incredibly important concept. Okay? So again, it's a measure that is used to quantify the amount of variation in data. We're looking at how consistent the data is. Now you'll see here a formula written. Yes, I want you to write it down. So go ahead, pause the video and write it down. But we'll talk about it in a second. So pause the video, write it down, and we'll get to it. Now, as I mentioned before, standard deviation produces a number, but how do we interpret that number? Well, the larger the standard deviation is, the less consistent the data will be. What does that mean? That means if my standard deviation is a really big number, my data is not consistent. It's very spread out. It's all over the place. It's the second list up here. The second list would have a larger standard deviation than the first list, okay? The smaller that standard deviation number is, the more tightly packed or consistent that data would be. Okay, so now that we've got that, again, if you're confused at this point, hang in there, pause the video, send me emails about what's confusing you if you want more explanations on a definition. But let's get into the formula, okay? We know what standard deviation is. It's going to tell us how consistent the data is, but how do we calculate it? How do we find standard deviation? Well, you're going to use it by this formula. Like mean, there's a difference between the formula for sample standard deviation and population standard deviation, just like there was sample mean and population mean. The calculations are very similar, but the formulas are going to look a little different. We are going to start by learning about sample standard deviation. Now you've written this formula down at this point, but you might be puzzled. You go, I don't even know what half these symbols mean. How in the world is that going to tell me how consistent a set of numbers is? Well, let me break it down for you. We're going to take some math theory and we're going to break it down. Where does that formula come from? And how are we going to figure out how consistent data is? Well, here's what statisticians did. They started with an X. What is X? X stands for your data value. If I have 5 pieces of data, X could resemble any one of those. I could plug them in for X, okay? A variable, X is a variable. It's just a placeholder for data. No big deal, okay? It's a given data value. Now, why in the formula do we see this X minus X bar? You might be thinking, X bar? Wait, you know that from 3.1. X bar, remember, stands for the sample mean. So why do we do this? Well, if I subtract a data value from the sample mean, it tells me the difference between the two. And this gets at the consistency piece. If I have a data value that's very far from the mean, that subtraction is going to produce a big number. But if the data value is very close to the mean, it's going to produce a small number. The more data that's closer to the mean is going to produce data that's very consistent. Data that's far from the mean is going to be inconsistent. So in this formula, we are going to subtract our data value, or we're going to subtract our mean from our data value. Then what do we do here? Well, you can see in the formula, the next step to this is, okay, I'm subtracting all my data values from my mean to find the difference, but then I square it. Why do you square it? Well, we square it because we don't want negative numbers, right? Negative numbers would cancel out each other. If I had 5 minus 3, if my mean is 3 and one of my data values is 5 and I do 5 minus 3, I get 2. But if I do 1 minus 3, I get negative 2 if another one of my data values was 1. Well, they both have the same distance from the mean, so as far as consistency goes, they'd have the same level of consistency, right? One's 2 below, one's 2 above. Well, when you square that subtraction problem, it eliminates the negatives. Okay? And then what we're going to do is we are going to throw this fancy looking E in here. This symbol means sum. So essentially you do all those differences, all my data values, I subtract from my mean, square it to make sure there are no negatives, and then the sum symbol means add them all together. So I'm adding together all the differences, right? The squared differences, okay? We got all these numbers. If they're big, it means we're far from the mean. If they're close together, it means we're tightly packed with the mean. I square them all to get rid of the negatives, and then I add them all together. And then, kind of like you do when you calculate the mean, we're going to divide by however many there are, specifically n minus 1. N is how many data values there are. So let me write some terms here for you. This is a sum. This stands for data value. Remember, this is the sample mean. And this stands for the number of data values. So just like when you calculate mean, you add them all up, divide by however many there are. Well, we added all our stuff up, a little more complicated, but we added all our stuff up. We're going to divide by however many there are. Okay? And in doing this, this gives us our variance in our data. This formula right here, and I would pause and write this down, is the variance in data. And you've seen me throw that word around. Variance, it's the spread of the data. Okay? And then finally, to get standard deviation, we take the square root of it. We square root the variance and we get standard deviation. Okay? So you might be going, Mr. Carter, my brain hurts. This is way too confusing. This is way over my head. I thought we were just talking about mean, median, mode. It'll be okay. Let's do an example together. Let's calculate standard deviation together. By the way, where can you find this formula? Do you have to have it memorized? No. But one time, it is on your formula sheet, okay? If you go on that formula sheet and look for sample standard deviation, you will find it there. So to summarize, where are we at to stop your brain from hurting? Well, we're trying to find consistency in data. We don't want to know what the middle is of the data always. We just want to sometimes know how consistent it is. How much does it vary? The good measure for that is standard deviation, and we just learned the formula for it. So let's apply it. Blossom Greenhouse was commissioned to develop an extra large rose for the Rose Bowl parade. A random sample of blossoms from hybrid egg bushes yielded these diameters for mature peak blossoms. And I'll give you some measures here. 2, 3, 4, 5, 6, 8, 10, 10. 2, 3, 4, 5, 6, 8, 10, 10. Okay? And we want to find how consistent this data is. We want to find the standard deviation. They're developing an extra large rose, random sample, produce these diameters. What is the consistency? Okay? Or the variance. Well, first things first, what's our formula? Well, let's write that off to the side. Our standard deviation, remember, is the square root. Got the sum of x minus x bar squared. That's going to be divided by n minus 1. Well, in order to do this formula, I got to come up with some pieces of information. Number one, I need all the data values, which we have here. 2, I need to figure out the sample mean. What am I going to do? Well, I'm just going to find it by adding up all these data values and dividing by however many there are. So in a calculator, I'm going to do 2 plus 3 plus 4 plus 5 plus 6 plus 8 plus 10 plus 10. 48 divided by 1, 2, 3, 4, 5, 6, 7, 8, and I get 6. Okay? So my sample mean is going to be 6. Sample mean is going to be 6. Now what I'm going to do is I'm going to have to take every data value and subtract it from the mean and then square it. Subtract it from the mean and then square it. So that's what x minus x bar squared means. Okay, take every data value, subtract it from the mean, and square it. So to do that, I'm going to do 2, my first data value, minus 6 squared. And 3 minus 6 squared. You get the idea. Again, please write this down. Okay, we're working inside out in this formula. Okay, so what am I going to do here? Well, I got to do 2 minus 6 squared, and I get 16. 3 minus 6 squared is 9. Again, I'd pause the video, try this on your own, make sure you're getting the same data values as I am. 4 minus 6 squared is 4. 5 minus 6 squared is 1. 8 minus 6 squared is 4. Again, if you go back to the theory part, the whole reason we square it is so that 4 minus 6 and 8 minus 6 give us the same distance from the mean. 10 minus 6 squared is 16 and 16. Okay, so what we've done so far is we've taken care of this part of the formula. Now we can handle the sum. What does the sum say? It simply says you took every data value, you subtracted it from the mean, and you squared them all together. Now add all those values up. So in my calculator, I'm going to do 16 plus 9 plus 4 plus 1 plus 4 plus 16 plus 16, and I get 66. So where we're at in our formula right now is I've done the whole top row. Check. So I've still got a square root to deal with, but the whole top row comes out to 66. Again, if you're confused, pause the video at this point, shoot me an email and let me know. All right. Remember, n stands for how many data values we have. We have 8. 8 minus 1 is 7. And so I'm going to calculate the square root of 66 over 7. And when I do that in my calculator, I get 3.07 if I round. That is the standard deviation. Okay? Again, what is standard deviation? A measure that is used to quantify the amount of variation in a set of data values. So the standard deviation here is 3.07. Okay? If you need a break, if your head's hurting, if you need to stop for a moment, pause the video and go do practice problem number 1. If you go on Schoology and look at the practice, you should be capable of doing number 1 at this point. If you want to keep plugging along with the instruction though, that's okay. Stick with me, okay? But if you need a break, pause the video, do number 1, come back and watch the second half of the video. All right. What is the sum of squares? Sum of squares is not the most important term in the world. It's just a term you might see, so I want you to be familiar with it. It refers to the top half of the fraction in standard deviation. It's the top half of the fraction when finding standard deviation. Okay, what is that practically speaking? Sum of squares is this, the sum of x minus x bar squared. Whatever that comes out to is the sum of squares. It's used in other statistical measures. We won't use it autonomous class by itself. We'll only use it as part of the standard deviation formula. In the problem we did, 66 would be our sum of squares. Okay, you can see it right up here. Sum of squares. Okay, Sum of squares. All right, so you've now learned how to calculate standard deviation. Remember earlier I said there was sample standard deviation and population standard deviation. So here's the formula for population standard deviation. Sigma equals the square root of x minus mu squared divided by capital N. What's the difference here? Well, I hope you recognize that the formulas almost look identical. Again, this will be on your formula sheet. Here's what, I'll write the formula for sample standard deviation below here in blue so we can compare. And I hope you notice they're almost the same. We just have a couple technicalities. Number one, for population standard deviation, you're going to see sigma, that funky looking O with the hook at the top, instead of S. Okay? The Greek letter sigma stands for population standard deviation. S will stand for sample standard deviation. You also notice the X bar is replaced with mu. Why should that make sense? Well, mu is the population mean. Remember? Population mean. X bar is the sample mean. So it's fitting that we switch out X bar with mu when we're working with population standard deviation. Okay? Finally, you'll notice the denominator, one has a capital N, the other has N minus 1. That's just a technicality. Capital N is the population amount. That's the number in the population. Little n is the sample, the number of samples there are. And capital N is the number in the population. Subtracting 1 is a statistical, it's just a statistical difference that we do. It's a little above this class why we use n minus 1 versus capital N, why we don't do capital N minus 1, but you don't need to worry about that. Again, just notice the slight difference, the technicality between subtracting 1 with the sample and not with the population. Okay. You're probably sitting there going, Mr. Carter, there has got to be an easier way to finding standard deviation than doing all this. And you're right. There is. Okay? I need you to know how to do this. I believe we're going to have you do this on your first test. Why? Well, it might seem tedious, but I want you to know the thought process behind standard deviation. Not just what it is and memorizing the formula, but why does it prove that there's consistency? It's why I talked you through the formula up here. Okay? But for the sake of time, as we move on out of chapter 3 at some point, right, we don't have the time to, nor do we have the energy to do this by hand every single time. So how do we do it with a calculator? Well, you need to have a TI-84 for this. If you are someone who borrows one of mine, that's fine. You can do it on there. But you do need to have a TI-84 to have access to this. So how do we do this on a calculator? Well, let's say we have this list of data and we want to find the standard deviation. Remember, we should come up with 3.07. So what I'm going to do is I'm going to, here are the steps in the calculator. This is on your formula sheet, but I still would like you to write it out. First thing you're going to do is you're going to click Stat. Okay? It's a button that's in the second row of your calculator next to the left arrow key. Then what you're going to do is you're going to see a screen pop up that says Edit. Go ahead and click Enter. So I want you to click on Edit. And you're going to see these things that say L2, L1, L3, etc. Essentially, these are lists in your calculator. L1 stands for list 1. L2 stands for list 2. And what I want you to do is I want you to enter the numbers into a list. So all I'm going to be doing on my calculator is I'm going to hit 2, enter 3, enter 4, enter 5, enter 6, enter 8, enter 10, enter 10. Okay, I enter the data values into my list. Then what I'm going to do is I'm going to hit the Stat button again. And what it's going to do is it's going to take me back to that edit screen. Okay? Except I'm not going to click edit this time. I don't want to go back to the list, but I'm going to tab over with the right arrow key to calc. And then there are going to be a bunch of different options, and I'm going to click enter on first bare stats. Okay, and then it'll take you back to the home screen of your calculator. And then what I want you to do is I want you to hit the second key. And then if you look on all the, I want you to hit the second key, and then you're going to click the stat button again. And what you're going to do is you're going to see a bunch of your lists pop up. Okay? A bunch of your lists are going to pop up. It says names. Okay? And it'll say L1, L2, L3, L4, L5, and L6. What I would like you to hit is, I want you to click on whatever list you entered the data in. So if you entered the list in L1, click L1. If you entered the list in L3, tab down to L3 and click enter. So you're going to click on the list you want. And then finally, you're going to click enter. And don't touch anything, then a bunch of data is going to pop up. Okay? These are your first variable stats, and what I hope you see are some key features. The first thing you should see is x bar equals 6. What is that? That's your sample mean. We calculated that earlier for this list of data. Then you're going to see the sum of x, so that's adding all your data values together, which is 48. The sum of x squared, if I square the sum of all my data values, and then you see s of x. And that number, 3.07, is the exact same as what we calculated earlier. This is the process for finding standard deviation on your calculator. We are going to do it a million times. You need to know how to do this. Write down these steps. Pause the video at this point and try it on your own. Enter your own list of data and make sure you can get the standard deviation. Okay? Very important. Now below you'll see sigma of x. And it's going to be close to that 3.07, but it's a little different. This is your calculator's population standard deviation feature. We will not be using it. When we calculate the standard deviation, we're always going to calculate the samples. So make sure you choose S of x. But this is how we find standard deviation in the calculator. Okay. Take a breath. We're almost there. We got a couple more concepts to go over, and then we'll be okay. Next concept is the coefficient of variation. What is that? Well, this displays standard deviation as a percentage of the sample or the population mean. What are your formulas for that? Well, if we're looking at a sample, it's going to be our sample standard deviation divided by the sample mean, or x bar, times 100. Again, the times 100 turns it into a percentage. And essentially all we're doing here is we're taking our sample standard deviation and dividing it by the mean. If we get a big number, the bigger the number is, the bigger the coefficient of variation is, the less consistent the data is. The smaller that number is, the more consistent the data is. If we wanted to do this for the population, we would do sigma divided by mu. Again, that would be my population standard deviation divided by my population mean times 100. Okay? So, let's run an example. Kind of tying the whole deal together. Let's say I had this list of data. What I want to do is I want to find the mean and the standard deviation so I can find the coefficient of variation. I'm trying to find the coefficient of variation here. Well, what's the formula? X bar. This is a sample list. It's, excuse me, I wrote that wrong. It is S divided by X bar times 100. Well, I got to find S and X bar. Well, let's do it the quick way. Let's use our calculator. So how am I going to go about this? Well, remember, again, I'm going to talk you through it. Go to the middle of your calculator and click that stat button. Click edit. Again, if you need to see the steps, they're right here. Click the stat button. Click edit. You should have those steps written down. Then we're going to clear our list, or you can use a different list. How do you clear a list? Go ahead and click clear, which is just below the lower arrow keys. Tab up so it highlights the list. Click clear and then click enter. It should clear your list, or you can clear the entries individually. Once your list is empty, go ahead and type in those data values just like we did before. And when we do that, we should end up with 1, 2, 3, 4, 5, 6, 7, 8 data values. Okay, now click Stat. Well, we're going to go over to Calc. Click Enter on first variable stats. Click Second. Click List or the Stat key. Enter the list you had, and then click Enter again. And what we see is we get our X bar. We get our X bar, which is 2.13125. And our S of X, 0.237, I'll stop at 5. So we get quickly our sample standard deviation and our mean. The mean of this list of data is 2.13 with a standard deviation or a consistency level of 0.2375. If we divide 0.2375 by 2.13125 and multiply that by 100, we're going to get about 11%. About 11%. Okay? So that is how we find the coefficient of variation. Again, the higher that number is, data is not consistent. The lower that number is, pretty consistent. Last thing, last concept. Chebyshev's formula. What is Chebyshev's formula? Well, remember, standard deviation is the amount of variance in our data. So what does Chebyshev say? For any set of data, either population or sample, and for any constant k greater than 1, the proportion of data must lie within k standard deviations on either side of the mean is at least 1 over 1 minus k squared. And you were like, Mr. Carter, you have already confused me enough today. That makes no sense. Let me talk you through it. Okay? For any set of data, the percentage, when you see proportion, I want you to think percent. The percent of data that is within k standard deviations on either side of the mean is at least 1 minus 1 over k squared. What is the heck does that mean? Let's say this is the spread of our data. Okay? Picture it as a curve, if you will. The mean is right there in the middle. Okay? This is the mean. So we've got a curve of data. You can imagine my most extreme points are out here. Most of my data is right in there. Okay? Well, what the heck is a standard deviation? Well, standard deviation is how much we expect the data to vary. Okay? So a standard deviation could be out here. What does that mean? One standard deviation, remember a standard deviation is how much we expect the data to vary. One standard deviation away from either side of the mean would include all of this data. Two standard deviations away from the mean would include all of this data. Again, the standard deviation is the expected amount we're going to vary. So what the heck does Chebyshev's formula mean? Well, for any set of data and for any constant k greater than 1, the percent of data that has to be within k is just going to be a number. Standard deviations on either side is at least 1 minus 1 over k squared. The best way I can talk about it is with an example. This means for any set of data, at least 75% is between two standard deviations above and below the mean. So if this curve represents my data, if I have a set of data, that has a mean of 2 and standard deviation of 1, then what this formula says, if the mean of the data is 2 and the standard deviation is 1, then I can guarantee, so this would be what? 3 and 1, 4 and 0. This means for any set of data, that means 75% of the data, at least 75% of the data, is between 2 above and 2 below the mean. So what Chebyshev's essentially says is if your mean is 2 and your standard deviation is 1, and you go 2 standard deviations out to each side, so if the mean is 2 and the standard deviation is 1, and I go 2 above, that's 4, 2 below, that's 0, 75% of your data is going to be in between there. Minimum. If I would go 3 standard deviations away, so -1 and 5, 88.9% of my data will be at least between those values. So I have a mean of 2, standard deviation of 1. I don't care what data set you have. If that's the mean and the standard deviation, I can guarantee you that 89% roughly of your data is between -1 and 5. If you have any data set that has a mean of 2, standard deviation of 1, I can guarantee you 89% of that data is between -1 and 5. That's why this formula is so powerful. It can tell us how much data is between certain points with a huge degree of accuracy. And not just for curves like this, but for any curve of any shape and any size. Where do these percentages come from? This formula right here. Chebyshev's formula, 1 minus 1 over k squared, where k is a number. So how does that look here? Well, think about it. Let's look at I told you that 2 standard deviations above and 2 below, at least 75% of the data, according to Chebyshev's, will be between those 2 values. How do I know that? Well, when he says 2 standard deviations, you plug in 2 for k. If you do that, you get 1 minus 1 over 2 squared. What is 2 squared? 4. 1 minus 1/4 equals 3/4, which is 75%. If you did it for 3 standard deviations, you're going to get 1 minus 3 squared, that's 1 minus 1/9, aka 8 over 9, which is 88.9%. Okay? Chebyshev's formula is huge because it guarantees how much data is between 2 values. That's what you need to remember for Chebyshev's. Remember the 1 minus 1 over k squared formula. but it guarantees how much data is between certain amounts of standard deviations. Okay? I can guarantee you that if I have a mean of 2 and standard deviation of 1, 75% of my data is between 0 and 4. At least. Could be more, but at least that many. Okay? So what do I practically need you to do with Chebyshevs? What am I looking for here? Well, let's say we had a sample mean of 29.1 and a sample standard deviation of 1.7. We are going to find an interval so that 75 of the students fit in this program. Okay? We have a sample mean of 29.1, sample standard deviation of 1.7. We're going to find an interval which 75% of students fit in this program. So we could imagine this is a graduate school program, and this is the average age, 29.1, with a standard deviation of 1.7. And we want to find a range of numbers so that 75% fit in the program. So how are we going to do this? We'll use Chebyshev's formula. What did Chebyshev's formula say? It was 1 minus 1 over k squared. And it guaranteed that at least the proportion of the data must lie within k standard deviations on either side of the mean is at least 1 minus 1 over k squared. Okay? So what are we going to do here? Well, when we look at this, we saw earlier that when you use 2, any set of data, at least 75% is between 2 standard deviations above and below the mean. So if k is 2 standard deviations, we get 3/4 or 75%. So what do you need to apply here? Well, again, the problem asks us to find an interval for which 75% of the students fit in the program. What that means is 2 standard deviations, according to Chebyshev's formula. If I go 2 standard deviations above the mean and 2 below, 75% of the data will fit in the program. Again, that's right here. Any set of data, at least 75% is between 2 above and 2 below the mean. So when you have a mean of 29.1 and a standard deviation of 1.7, well, if I draw that curve again, 29.1 is my mean, and I go up by 1.7, 1 standard deviation above is going to be 30.8. 1 standard deviation below 29.1 minus 1.7 will be 27.4. But I need to go 2 standard deviations. Why? Because according to Chebyshev's, at least 75% of my data will be included between 2 standard deviations away. So I do it one more time. 30.8 plus 1.7 is 32.5. 27.4 minus 1.7 is 25.7. And what that means in the grand scheme of life for us is we've gone 2 standard deviations above and below the mean. Thus, my answer would be 25.7 to 32.5. Because Chebyshev's formula tells me that for any set of data, 75% is between 2 above and 2 below the mean, all I have to do is take my standard deviation and add it twice and subtract it twice, and I can guarantee you that 75% of the data will fit between these values. So in the context of our problem, if the average age of someone in the graduate school program is 29.1 with a standard deviation of 1.7, and I want to make sure 75% of the people fit in this program, I need to grab ages between 25.7 and 32.5. Okay. It's been a lot. You probably need a nap right now. Very dense chapter. Please come to me and ask questions. Take a break for the day. It's why the only job for you today is to watch this video. Email me questions. We'll go over them in person. We'll get it figured out together. Just your job in the video is to take good notes. So if there's anything you didn't take good notes on, go back, pause the video, and take good notes on it. But otherwise, have a great day, and you'll be all right.